This is your experiment number 8. Okay, so in last class what happened, I discussed about different DC-DC converter, okay, and their simulations with in open loop system, okay, where we have discussed about buck converter, boost converter, then asymmetrical bridge, symmetrical bridge. But in this study we are going to discuss about the basic closed loop control of DC-DC switching converter by using NI multisim. Okay, so basically you know that what is the motivations of the closed loop control. So you know that one motivations of open loop system. Definitely there is some motivations. Normally we have studied the open loop systems based on need to know about the means parameter system identifications, okay, for the open loop studies. Okay, so basically what do you mean by that open loop study? So you know that DC-DC converter having the switching non-linearity, means it's totally based on when switch is turned on and when switch is turned off. Okay, so that means if you vary the duty cycle, okay, so that means if you are going to vary the duty cycle, so your output will be varied. Okay, that's the basic convention. So you know the expression of the output voltage in terms of duty ratio for the buck converter as well as boost converter. Today I have discussed about the full bridge converter. Okay, what will be the relations of your duty ratios and your output voltage instead of input voltage. Okay, whatever voltage you have applied to there, that side. Okay, so what is the motivations? So first, from the open loop study, if we vary the duty cycle from 0 to 100%, okay, so you will get what will be your minimum voltage minimum output voltage and what will be your maximum output voltage. Okay, so in average, basically it's a DC-DC converter, means it's an example of a chopper. Okay, so average output voltage with the variation of the duty ratio, how it will be changed from minimum to maximum, that you have to find out. So then what is the meaning of the closed loop control? So in case of closed loop control, what happened? If you see open loop system, so initially it was in cutoff region, then you can see it will be in saturation region. So in the meantime you are getting that quasi operative region. Okay, so that means where it will be in linear mode of operations. Okay, more or less gradually increasing if you are able to draw the transient. Okay, at that point what happened, you can find out at the region and try to regulate your output voltage with the variations of any kinds of with the applications of any kinds of disturbances. Okay, so that's the motivation of the closed loop control. Somehow you can take one example. So I am telling about your DC-DC full bridge converter. So it's a chopper, 4-quadrant chopper example. So you can see that where you can implement that 4-quadrant chopper in case of DC motor speed control. Okay, so what is the input of the motor? Input is your electrical energy and output is your mechanical energy. Okay, so in this case, what is the input of the, what is the output of the chopper? So you have given some of the input voltage of the DC-DC converter, means chopper, means it's a 4-quadrant chopper. So if you vary the gate pulse, so what happened? The chopper output voltage that I am telling you now, to measure that value is a digital multimeter. Okay, or digital voltmeter, that value also been changing with the variations of the duty cycle, but that duty cycle should be function of your motor speed. Okay, how it will be the function of the motor speed, that I am going to be discussed. Okay, so if you vary the duty ratio, then what happens? Chopper output voltage, output average voltage will change. Okay, that output average voltage will change means input of the motor also will change. If you are using a DC motor as a load or as a as a load of the 4-quadrant chopper in that case. So if you vary the input voltage, means your load voltage also mean varied. Input voltage. If you vary the duty cycle, means your load output average voltage also will vary. That means input of the motor load also will vary. Okay, if the input of the motor load is vary, so motor having 3 modes of operations. Normally in speed control there are 3 methods: input voltage control, armature voltage control, another one is field control. Now I am only focused about the input voltage control or armature voltage control. Okay, if your armature voltage control is if your armature voltage is varying, so definitely the motor speed will be vary up to 0 speed to maximum base speed, means rated speed. So what happens if the motor shaft is connected through a tacho generator? Okay, then what happened? The tacho generator, what is the purpose of the tacho generator? Tacho generator is a transducer, so that it can convert the RPM to your equivalent voltage, but that voltage level is very less. Okay, so you have to amplify that voltage value. Okay, that's why some amplifier circuit is there. So to scaling down that output voltage of the tacho generator, and you can compare that voltage with some reference value. So from this circuit you can see that one reference DC value is given. So it's an example of a buck converter. Okay, closed loop buck converter in voltage mode control. So one voltage is there. Okay, same kinds of happen in case of motor control, 4 quadrant operation of the DC motor. Okay, so that voltage is your reference voltage. You know the basic structure of the control system. So normally you are giving as an input, means as a reference input, then there is a differential amplifier. Okay, that differential amplifier is comparing your reference input and your actual output. Actual output means you are getting the output from your system. Okay, so that output is scaled down, and it should be the comparable with your reference value. Okay, if your reference value is 5 and your output you have get over there is a 0.1 volt, so definitely it should not be comparable. So you have to scaling down that value. Okay, so that voltage value, in case of tacho generator, that value will be less, so you have to scaling down up to your reference voltage value. That reference voltage value should be equivalent voltage value of your equivalent motor speed. Okay, so somehow we are considering 1500 rpm means 5 volt, you have considered like that. So your tacho generator voltage you should be scaling down according to that value. Okay, so it should be in the range of 5 volt, maximum it should come 5 volt. Okay, anyhow that voltage is coming, now you are comparing that value. Okay, so like your control system structure, so after comparing we will get some error value. That error value should be passed to the controller. Okay, then controller means you will get some control signal from the controller. That control signal compare with some repeating sequence. Okay, that you know that in gate driver circuit you have already simulated that circuit for non-isolated and isolated. You are comparing the triangular waveform with some pot value, means reference value, similar thing. So that pot value means here you are getting the control signal from your speed, motor speed. Okay, that value will be compared some repeating sequence, and after comparing the repeating sequence you will get one PWM. Okay, that PWM will be passing through the driver circuit, and that driver circuit PWM will be feedback to your MOSFET of your MOSFET, maybe whatever switches you have used for your DC-DC converter. Okay, so that's the operation. So that's the closed loop operation of a 4 quadrant chopper fed motor. Okay, so that if you speed is varying, so that gate pulse, that means the DC value, that means control speed is varying means error will be varying. Basically reference value is fixed, so actual input is coming, actual input is coming from your motor speed. Okay, so that also being varying. If it is varying, so error signal, basically differential amplifier, so comparing with your reference and that actual value, so both are varying. Sorry, reference is fixed and actual signal is varying, so your error will be varying. If error is varying means error is passing through the different controller, so control output also being varying. If it is varying means your the DC value also being changing but repeating sequence is fixed, and the frequency of the repeating sequence is decide the frequency of your switching device. Okay, so that varying of that control signal means the PWM also been change, also been varying, and as per the variation of that value you will get the output. Okay, converter output. According to that output, again the motor input voltage. Okay, basically output means converter output means armature input voltage, that also being changed. Okay, then again motor will be regulated. So by that way you can regulate the entire system. Okay, here we are showing two circuits. Okay, voltage mode control of DC-DC buck converter first, then we have discussed about the voltage mode control of DC-DC boost converter. So previous experiment we have studied about only the open loop. Okay, so here open loop means you are directly giving the pulse, but here we are discussing about the closed loop signal. Okay, so you know the basic structure of the buck converter. Input voltage is there, 10 volt. Okay, just wait for a moment. Sorry. So here you can see that one. So it's a basic structure of the buck converter. So it's your MOSFET IRF P450 MOSFET is there. So 10 volt you are given. So mood diode is there. It's your current probe, and 1 ohm is the ESR value of the inductor, and 100 microfarad is the sorry 10 milliohm is the ESR of that 100 microfarad capacitor, and load resistance is 20 ohm. So you are given that 5 volt as a reference, so your output should be coming, okay, should be coming nearer to the 5 volt. Okay, so here you are giving that voltage dividing circuit. So here you can see one voltage dividing circuit, and you are getting that value, scale down that value, and it is fed to a differential amplifier. This is your differential amplifier, that means TL084, and your reference voltage is 5 volt, and it's your differential amplifier passing through a PI controller. It's the structure of PI controller. Okay, that RC and R. Okay, in your feedback path that RC circuit network is there, so it's in structure of a PI controller. You can get also the transfer function of that circuit. Okay, you know that output means VO by V in equal to that RF 1 plus RF by Rin. Okay, so here ZF by Zin. ZF equals to what? That is R. So ZF equal to, you know that it is R plus omega, sorry, XC. Okay, so it's a capacitor. So R plus 1 by sorry, R plus X equal to 1 by omega C. So by that way you can calculate the transfer function of the PI controller. Okay, so then after the PI controller you will get the control signal. Basically that value will give you the error differential amplifier. So first you will get the error, and that error is passing through the PI controller, and you are getting the control signal here at terminal 4. Okay, so at the here you can see terminal, sorry, here you can see the terminal 3 of that LM311. Okay, LM311 is a comparator. Okay, so here you are giving a terminal 2 and terminal 3. So input, reference input you have given, positive reference input you are given in terminal 3. Okay, and control and actual voltage means scale down actual voltage is coming terminal 2. Then you are giving the bias voltage. So 11 is the negative terminal, so you have given minus 15, and 4 is the positive terminal, you are given plus 14. Sorry, plus 15. Okay, then you are getting the control signal. Now the control signal is comparing with your repeating sequence, means triangular sequence. So it's a function generator. It's a function generator. So the function generator having the switching frequency is 5 kilohertz. Okay, you can set also 10 kilohertz, 20 kilohertz, whatever you are asking, and your amplitude, maximum peak to peak amplitude is 15. Okay, so 15 volt. So then you are comparing the control signal with your repeating sequence. Okay, again that negative terminal means here you are giving that page connector is there. For that I have prepared that page connector. So here you can see 15 volt positive terminal is grounded and negative terminal is grounded here. So P positive means you are getting the positive one, and it's a reverse polarity. V means you are getting the minus 15 volt. Okay, so that I am given here, and it is again it's an comparator. After comparing you are getting the PWM. That PWM is fed to the IRF 450 MOSFET through one additional resistance, that is 470. What is the purpose of this resistance? MOSFET is a voltage driven circuit. Okay, so that's why the additional resistance you have to provide here to reduce the current strength. Okay, so it's a voltage divider circuit for scaling down that value. Okay, whatever voltage you are getting, that is coming from your open loop study. Okay, so first you have to give the 50% duty cycle. So what voltage is there? Okay, so whatever voltage you are asking, first set it there, and as per the value you can scaling down. Okay, scaling down through the voltage divider circuit. So it's a voltage mode controller, DC-DC buck converter with PI controller. So here you know that we have using some MOSFET, everything we have discussed here. So that what are the values are there, and as well as their value I have mentioned here. Okay, so purpose of that study you can understand. Then you can see that one that is that's a repeating comparison of your, that pink color line is your control signal line. Okay, and this is your short tooth, or you can say like the triangular waveform. Okay, triangular waveform it is given. Okay, now it is comparable. So if it is comparable, you will get some PWM. The PWM I have not given, the diagram I have not given, but you keep it in your study. If you keep it in your write up, that PWM value. Okay, so how it will be look like that PWM. Okay, so then we'll get that voltage and current response here. Okay, so both the cases, that transient one you can understand. So around the 5 volt. Okay, some peak overshoot is there, but it is fixed up with the 5 volt. Basically, why 5 volt? That you have given reference as a 5 volt. Okay, so output should come as the value of the 5 volt. Okay, in the range of the 5 volt. As your reference is given 5 volt, current also getting as per the value. Then same study we can go for the boost converter. Okay, so in case of boost converter, same, the structure is the boost converter, then we are sensing the actual output voltage, then we are comparing it with your 5 volt reference value, then PI controller values are given here, then we are comparing entire the thing, and a function generator is there. Okay, then you can see the comparison. It's a triangular waveform, and compare with the pink color waveform is your control signal waveform, and the triangular is your repeating sequence voltage. Okay, now we will get the transient response. Okay, so 5, again it should come the 5 volt, green color value is there, it is in 5. Okay, still it's a boost converter, but output you have regulated to 5 volt. Okay, basically scale down output. Here you are getting that value is the scale down output. Okay, so that value is coming at the 5 volt. Okay, so as per the efficacy of the controller, that overshoot and steady state error will be maintained. You know that there is some overshoot. Okay, so 5 is your reference value, but you are getting the overshoot up to 7 volt. Okay, nearer to the 7. Okay, so how much percentage of overshoot is there? 7 minus 5. 7 minus 5 divided by 5. So it is coming by 40%. It is coming nearer to 40% overshoot. That means the PI controller is not giving the good response. Okay, 40% overshoot means it's not giving the good response. Okay, so you have to tune the PI controller also. Okay, here from figure 5 you can understand the comparison between the control signal and the triangular waveform of the boost converter in multisim, and it's your dynamic response. Okay, or the closed loop response of a output voltage. Okay, output voltage and inductor current. Okay, inductor current of boost converter in converted in multisim platform. Okay, I think all of you will to understand the theory. All the specifications are given in the table, and some small theory I have also mentioned here. You can go through it, and you can also follow any of the standard power electronics book to stronger to concrete your theory. Okay, so I think you are able to understand. Now I am requesting Ramaprasad sir to share his computer screen to show some reference simulation. Am I audible, Ramaprasad, from your side?
Yes, sir.
Yes,
Yes.
sir. Okay, please share your computer screen so students can see their simulation. See your simulation.
Visible? Students, is it visible to all?
Yes, sir.
Yes. Now this is your circuit. Sir already told.
Can you please zoom in? Ah, yes.
First part you check 10 volt supply source, and as you have previous experiment, same switching device, the IRF 1010 N diode. This one I've taken. So as per your circuit diagram, sir already shown in manual. These connections are made. Okay, you can take the screenshots. Okay, then this is your controller circuit, PI controller circuit. Up to this you can see In manually page connector is given, but I have directly connected, and same components I have taken as per your circuit diagram. So first, using analysis, you will see the waveforms. You can also take this circuit screenshot. Okay. Then this is your function generator voltage setting, voltage and frequency. Okay. So first we'll go through simulation of this one, this second waveform. So this CRO is connected to this wire, that is 12 number. This net name you can see 12. So V12, and this one is V15. Net name 15, V15. So simulate analysis, transient analysis, output V12 and V15. V12, this one, and V15. So time is more. I have to take less time. Simulate analysis, transient analysis. This time you can take 0.01. Okay. And using cursor you trace the values. Then manually you can see the waveforms. You have to run this using grapher. Manually you can see the waveforms. Okay. You can do which method is convenient for you. By using both methods I have done. Similarly, go to this circuit waveforms. Here this is your net name 4. 4 means V4 is the voltage across the load, and this is connected to current probe. Net name is 8. I8 or IL, inductor current, series path. So in I8 or IL we can take. So go to simulate analysis and transient analysis. I8, IL, IL1 and V4. V4 is your output voltage across the load. V4, this one. Okay. I have given more time, no need to take this much. I can take less time. I have given more time. 0.01. A little bit more, 0.5. So separately you can see the waveforms by zooming this. and using this CRO you can see the waveforms. Simultaneously you can use the oscilloscope, not for this, sorry, it is the grapher of a second one. 1 minute. Grapher of first one. When we are doing that one, you first disconnect this CRO. Already you got previously, so no need of this CRO. Waveform not required here. Now the grapher will show this waveform. You have to change the scale ratio. Using analysis you can do this. Okay. I think grapher previously it was showing, but why it is not showing now? 1 minute. On one method already I have told you, and same method, similar method. This waveform is coming in your CRO, huh? But using grapher you can trace this. Where the grapher is not coming. One minute. Okay. No, this one is which one? Okay. Now again we will do this. You can do this using analysis, huh? And you can see the waveforms directly by this CRO as it's showing.
Ramaprasad sir, your computer screen is not visible.
Oh, 1 minute. Now is it visible?
Yes.
So this is your output waveforms of the CRO, and using this analysis already I have told you I have done previously. Using transient analysis you can see the output current through inductor and voltage, output voltage. Okay. So uh, same circuit I have done as per the manual. So only I have removed this page connector and directly connected this wave the supply source to the op amps. Okay. So
Okay, so I think students, all of you are able to understand. Okay, so Ramakrishna sir, please can you please zoom your circuit again?
1 minute. Previous connection was this. Okay. Uh,
Yes, please scroll up it. Please scroll it up. Yes. Okay, so first sir was discussed about the power circuits. Okay, that power circuit sir have already simulated based on that manual. Okay, manual means it's a reference, brief one. It's not the manual. It's a brief, just some idea on it. Okay, so the it's your power circuit. Okay, the next one is that please first one is your power circuit. Then please scroll down it. Then next one is your control circuit. So power circuit to control circuit, it is connected through a differential amplifier and reference voltage is 5 volt is given here. Then you have comparing them and you will get that a control signal, then control signal is varying with your function generator value, means your triangular waveform, and comparing both of them you will get the PWM, and PWM will fit to the MOSFET through a resistance. I think all of you will understand, there is no confusion. Yes or no? From students end? All of you will
yes, sir.
understand? Yes, na? Good. Okay, so I think you are able to solve it, means you are able to simulate it in your hostel. Okay, so buck converter simulation is simulated by the sir, simulated by sir. So next portion means boost converter simulation. You will do it in your hostel. So both the simulation you will do it in your hostel. Okay. So thank you. So today our
Attendance are
okay. So
taken.